It really is an honor to be here, along with the Grower Shipper Foundation. I really want to thank both CSUMB and the Grower Shipper Foundation for asking me to moderate this event and coming together around this topic. The other thing I would quickly say and congratulate is thanks for when you titled this the use of the word vision, because that's never been more important, and the four folks to my left really have great vision, see the whole playing field, and that's going to be important for the area economically, and then for the students in the audience as you envision your future. You're hearing from the folks that will be making it happen. I'm delighted to introduce Tom Rolander, to ask him to come to the podium as our keynote speaker. We had a chance to visit very, very briefly before the event, and what I was excited about and what I had always envisioned as the mayor, I had a very simple concept and really a question. What happens if we essentially rub the two sticks together of the innovation capital of the planet with the fresh nerve center in the planet? What are we going to get? And I think Tom Rolander really has some real insights to what that might look like as we go down the road. You know, he told me, I'm just an engineer who started to farm a little bit. And speaking as a loyal son of the Salinas Valley, that's exactly the playbook we all want to hear about. So with that, Tom, thank you. Welcome to CSUMB and Greater Vision.
Okay, it is a pleasure for me to be here in the Salinas Valley, connecting with the agribusinesses in the area and with CSUMB. I've spent the last 3.5 years commuting up to Silicon Valley to work at an indoor vertical farm. The irony of doing an 80-mile commute through the cultivated Salinas Valley to work in a warehouse did not escape me. So today, what I'm going to talk about is emergent technologies, some of the things driving changes that we're seeing take place in agriculture. I'm going to talk about first, what is the driving force? Why is this emerging technology accelerating at a rapid rate, particularly now at this point in time? I'll talk a little bit about how an engineer got into farming. I'll talk about a couple of kinds of innovation. We have incremental innovation, that's innovation that progresses along at a kind of expected rate. And then we have disruptive innovation, something that makes a major leap. And then I'll talk about what I believe to be an opportunity for the ag businesses here in the Salinas Valley. So the driving force behind emergent technologies, really it's addressing the problem of feeding the planet. We have a population that's just dramatically increasing, and that's a population that has to be fed. And one of the major resources required to feeding that planet is going to be water. So I'll be talking a little bit about water today. Probably many of you have heard of the name Malthus. He was an English cleric back in the late 1700s and early 1800s. And he was the first one to actually publish a paper and describe an observation that population was increasing exponentially. It was literally the hockey stick, growing up steeper and steeper, and that the production of food was increasing at a linear rate. And so what he foresaw, something that's been described as the Malthusian catastrophe. That's the point in time in which we no longer have enough food to feed the planet. So that's the genesis of what I believe to be this emerging technology. If we look at world population, these are UN figures. The estimates from the conservative to the more liberal estimates show something roughly 9 billion people by the year 2050. Right now, we're just over 7 billion people. I would guess that most of the CSUMB students in this audience will certainly live to see 2050. And so they'll see that 9 billion people. I looked around for some charts that could try and illustrate this particular problem, and I found this material from the United Nations. A few things captured my attention when I looked at this. The first was that 70% of the global water withdrawals are from agriculture. So agriculture is the biggest player in the field in terms of the water use. So that gets a lot of attention. Another one that I couldn't help but see on this is maybe the validating the trend towards a plant-based diet. Because we look at this and you'll see that there's a very heavy usage of water to be able to produce beef or other meat products. So that's just a sideline of this particular chart. Another thing that hit me is that the prediction is by 2025, that's only 10 years from now, there will be 1.8 billion people on this planet who have water scarcity. That is not enough water to live on. That could potentially produce something that you may have heard of called the water wars, which might well make the oil wars of this past decade or two look like child's play. So one of the issues with water has to do with management in agriculture. Water scarcity is an excess of water demand over that available supply. There are several ways that is being addressed. The first one is just to reduce the water losses, the evaporation, the runoff, and so forth. Second is to make the water go further, make the water use more productive. And last, to reallocate water uses to something more beneficial. And so that would be another way to reduce the demand. So let me get to the question of how Tom got into farming. Well, I've had a career that I spent as an engineer seeking paradigm shifts. I've been excited by major changes that I see evolving. A lot of times what characterizes those changes are that the business community doesn't believe it's really a rational, good business, and the technology community might not necessarily believe that it's a doable technology. When those two things come together, that's something that I'm very interested in. Early days of the first computer were that way. They were regarded as toys. Those of you that remember Byte magazine back in 1975, the cover of that magazine was titled "Computers, the World's Greatest Toy." So it was kind of a joke at that point in time. It was not something anybody took seriously. I best guess that everybody now no longer considers any of that with any humor. Next was getting into optical and electronic publishing. That was another major paradigm shift that led to now the information, the digital age that we're storing on the cloud. And of course, the internet is an enabler for that. So in the spring of 2012, I'd sold my last startup company, was getting ready to start another one. And a couple of things happened. One was I was introduced to a book by Peter Diamandis. He was the founder of the X Prize Foundation, the organization that sponsored that space race, the Spaceship One, and a really forward thinker. I'll show a video that he authored a little later in my presentation. So this was fascinating. His book was Abundance, the Future is Brighter Than You Think. So it was really addressing engineers, that we're going to save the world. And I thought that was pretty cool. Well, another thing happened at that time, and that was that I had a call from a neighbor, a friend of mine in Pacific Grove, Dr. Ko Nishimura. He called me and said he wanted to talk to me about an opportunity working for his company. Well, that company was Ecopia Farms up in Silicon Valley. And that was an opportunity that really did change my life and moved me into this new paradigm shift. So I've got a video here that I'm going to show.
Tucked into this unassuming warehouse in Campbell is the Silicon Valley version of farming.
Well, welcome to the farm. A little bit of Star Trek, a little bit of Willy Wonka.
Philip Folk is the Captain Kirk of this factory.
We produce wonderful things.
An inventor by nature, an engineer by nurture.
I worked for a company that built cell phones and PlayStations and networking equipment by the jillions.
What is a guy who comes from a tech background doing in farming?
I could not grow a houseplant to save my life. But this, I view it as an optimization problem, a production problem. So That I'm very good at.
Folks set out to solve one of the world's most pressing problems.
Water conservation is such a critical issue.
And under these red and blue lights, he thinks he may have the answer.
Plants don't need full sunlight to grow. Photosynthesis occurs only in a small band of red and a small band of blue. So that's all we give it. This is kind of like a plant spa. Things grow very, very fast in ideal conditions.
More than 370 lettuces, herbs, and microgreens start their lives here at Ecopia Farms.
Chervil and garlic chives, radishes and peppers. We're playing around with tomatoes. And this is the nursery. There's 340-some plants in each one of these.
Growing and harvesting happens year-round without worries about Mother Nature's whims or man-made waste. There's no excess water runoff and no pesticides. He hopes that in time, what took root in this Bay Area warehouse will sprout into a solution for a worldwide dilemma, growing an abundance of healthy, fresh food where land, water, and soil are scarce.
That's the magic of Silicon Valley.
In Campbell, Vicki Nguyen, NBC Bay Area News.
So I had my first meeting with Co, and then he brought me up to Campbell to tour the farm. I literally walked in the door and I was hooked. This looked like a great place for an engineer to come and have a wonderful time. So I got a chance to get my hands dirty. Well, those of my friends that know me as a person that doesn't do yard work. In fact, on my second date with my wife now of 34 years, on my second date, I looked at her across the dinner table, made eye contact, and I said to her, I don't do yard work. So 34 years later, I have been consistent in that. So you can imagine the surprise, first of all, from my wife, and then from all my friends when I announced that I was going to get into farming. Well, this was incredibly novel for me. I had a chance to go in and, as an engineer, actually get my hands dirty, to have dirt underneath my fingernails. As you can see from these pictures, I thoroughly enjoyed the experience. Well, I was responsible for the front end and back end IT, for all of the IT at the farm. And to do that, I felt like I actually needed to come in on the ground level and do literally everything, from sales entry all the way through planting, harvesting, watering, and so forth. So I got a chance to have a very novel experience in my career. Well, there's one story I have to take a digress to, and that is the application of the scientific method. Well, I was, as an engineer, totally excited about the fact that we were now controlling the entire environment. We were controlling the amount of sunlight, the amount of water, we were controlling pests. We were really applying a scientific process to agriculture. And so I had lunch one day and was sitting next to Dr. Dave King. He's a UC Davis ag professor who was a consultant, soil scientist who was helping with the farm. And I was going on about how we were going to just perfect the science of farming. When I finished my conversation, took a breath, he said, Tom, do you have any children? I said, yes. And he said, well, how many? I said, 4 children. Dave says to me, well, did you raise them all the same? Feed them all the same? Clothe them all the same? Love them all the same? I said, of course. He said, well, how'd they turn out? Well, that's a little simplistic story, but it does indicate that with biology, there's genetics involved, and you can't quite expect the same results from the same experiment every time. So let's look at some of the emergent technologies. The 2 areas that I'm going to talk about this morning are incremental, and those are things that we expect, small improvements. Generally what happens is things become cheaper, faster, smaller. So those things we expect is incremental. Disruptive really does change an existing marketplace and oftentimes removes a previous technology. How many of you still have VHS players? Probably not. Well, maybe a couple. Okay, all right. All right, proven wrong on that one. Well, they'll be around for a while yet. But anyway, certainly DVDs and now streaming online are replacing a lot of those technologies. Another area of disruption is exponential innovation, and I will get to that in the video a little bit later on. So in incremental innovation, there are 3 topics I want to hit in this. are the Internet of Things. You've probably heard that term. It gets a lot of buzz these days, and big data. And these subjects are something I struggled with. Were they incremental or were they disruptive? And they're actually aspects of both. Next is precision agriculture, and then cyber-physical systems. And I'll go into a little detail on each one of those. The Internet of Things is really about connecting literally everything you can think of. From your devices that you carry around, your mobile devices, anything you think of as computing, literally the light switches in your home, the garage door openers, the traffic lights, literally everything is in our life has the ability, or we have sensors, and then we also have actuators that come out and control things. And these are all going to be addressable in the Internet of Things. Not a very fancy name, but it certainly does describe this explosion of the Internet. Well, when you have all these sensors that are out there gathering this data, you now have huge amounts of data. Well, that great amount of data presents challenges in terms of its analysis. And so that's opening up whole new fields of that work with the big data. I'm going to get a little bit geeky on you for a second. This may be a term that you can use among your friends. Impress them that you know the difference between IPv4 and IPv6. If you have 5 is missing. Okay, IPv4 is the original Internet that was deployed in 1981. This had a 32-bit address space. What that meant was the original Internet could address 4 billion unique devices. So we could have 4 billion computers, 4 billion different devices that were connected. Well, it was pretty clear early on that was not enough of an address space, that we needed to get bigger than that. So what do you suppose happened? I think they may have overshot a little bit. They went from 32 bits to 128 bits. This is a number that's enormous. That's 16 billion. That's a 3 followed by 38 digits. That's possibly a big enough number for astronomers, and I've heard politicians, so I'm not sure. But anyway, it is a huge number. Okay, next, during my research for this talk, putting materials together, I was delighted to encounter a copy of the Californian last week, which had an article there about a team here at CSUMB led by Forrest Melton, where they're taking NASA satellite data and using it to measure drought, creating metrics to measure drought, measure the acreage that are going fallow each year. So that was just one use of that big data. So precision agriculture is all about making farming more efficient, producing more food, minimizing environmental impact out there, which is a good thing for the future of farming because you have to have an environment to do the farming, and then reducing the cost, making it cheaper for the consumer. Cheaper to produce, hopefully cheaper for the consumer. I have a video here that's going to illustrate a very new modern farm using precision agriculture and big data.
There's still a man in the driver's seat, but this combine steers itself by GPS. And there are still men in the fields, but this modern farm runs on big data. Everything on this nearly 20,000-acre Indiana farm is tracked, from the moisture of the soil to the precise productivity of every few square yards of corn.
Right there's the irrigation stop on the old Google map, and then here in a minute, we're about ready to enter it, we'll see our yield drop off. See it starting to drop down from 250.
With data streaming from soil sensors, combines, and satellites, Tom Farms manages an immense amount of information through its cloud computing system. It's all geared towards increasing yield.
So that future is already here. As you might imagine, it's a fairly expensive initial investment at this point in time. But we can only expect in the future that the costs will come down as the more and more of this technology is used and produced. And so that future will happen. It is happening. Next, I want to go into cyber-physical systems. This is really where we connect together the Internet of Things and big data. So we start in the lower left with an object domain. These are objects that are sensing. So they're sensing temperature, humidity, light, and so forth. This data is being gathered and put up into the cloud, into cyberspace. It then can be analyzed, because what's going to happen is that data is going to be used for actuation, for going down and controlling perhaps the amount of water or the amount of amendments or nutrients that are put in certain areas of soil of a farm. So this is the whole combination. It is a closed system, from sensors, taking the data, analyzing it, and going back to actuation. The next video I'm going to show you is, where is this emerging technology taking us? The Peter Diamandis that I mentioned earlier, he has a PhD from MIT and a doctor's degree from Harvard. So a pretty smart guy, and he's a real futurist. And he believes that the future direction of technology is leading us towards synthetic biology. And this is a brief video that will lead into his view.
This global network, or Internet of Things, will connect everyone and everything. And at the end of these connections will be an explosion of 1 trillion sensors, taking in images, listening to sounds, and measuring everything from vibrations to acceleration to temperature. The information gathered by these sensors will then be carried by the Internet of Things to AIs, which will then mine this explosion of data, allowing you to effectively know anything you want, anytime, anywhere. Perhaps this shouldn't come as much of a surprise, but the rate of technological progress is actually accelerating. After all, unlike the 2-million-year-old spearhead, the earliest mechanical computers, invented a mere century ago, have been doubling in price performance every 18 to 24 months, progressing from mechanical computers to relays, vacuum tubes, transistors, to today's integrated circuits at epic speeds. Computers are now 1 million times faster, 1 million times smaller, and 1,000 times cheaper than they were just 25 years ago. At this rate, over the next 25 years, computers will soon become microscopic in size, infinite in supply, and effectively free. This infinite computing power, along with artificial intelligence, will converge to transform the last, and certainly not least, disruptive exponential technology we'll be talking about, the field of synthetic biology. Every living organism contains the instruction code of DNA, written in 4 letters, A, T, C, and G, that directs everything. What proteins and carbohydrates the cell produce, and whether the cell is muscle, nerve, or skin. Today, with the advent of synthetic biology, DNA has become our new programming language. Using infinite computing and AI, we can design a sequence of DNA that will direct a cell to manufacture the perfect protein or carbohydrate to be used for foods, fuel, or vaccines. Far more tailored and efficient than ever before.
Pretty incredible view of the future of exponential technology. He talks even faster than I do. Let's look a little bit at disruptive innovation. And I believe that one of the focus that is taking place in disruptive innovation is moving farm production to the consumer. That's what the vertical farming and these other trends are. What we've had happen over the past hundreds of years is we have move people from proximity to where food is grown into the urban areas. It's because jobs are in the urban areas. So we've got a wider spread distance between those two. The disruptive innovation that I see, and I've been part of taking place, is in moving that farming into a location near the consumer. So there are several kinds of vertical farming. And the first kinds are without soil. These are water, with nutrients in the water. Hydroponics, aeroponics, and aquaponics. I'll show just briefly a slide on each of those. And then we have farming vertically with soil, which is what I showed in that video on Acopia Farms. So that was still in soil, and it was stacked shelves that Acopia Farms was doing. So vertical farming, hydroponics. This is the process of growing plants. Nutrients are provided through water and without soil. This particular photograph is of a building right now that's in Milan. This is the U.S. Pavilion at the Milan Expo. And the architect, when he put that pavilion together for this World's Fair, decided that what he wanted to do as an innovative approach to that architecture was to have an exterior wall that was in fact a vertical farm. And this is a hydroponic farm. Another form of hydroponics essentially is aeroponics. And that is using a mist to mist the root system of the plants. And so it doesn't use an aggregate or any other medium. You'll see here that the roots of this plant system are basically in air. They're just going to be misted. They're not in either soil or in water. The third form of this water-based vertical farming is aquaponics. This is the one I have the most difficulty understanding. This has got to be a very complex problem. I don't know how many of you have tried to keep a goldfish alive, but we're talking about having a fish in a tank, which are then producing waste. That waste is then delivered as nutrients to the plants. The plants filter that water, and it goes back to the fish again. Very complex system, but there's actually quite a bit of aquaponics going on these days. So I want to move into the focus of what I believe is my conclusion here. My insight from my experience as a IT person, as somebody involved with farming in Silicon Valley, is that agronomy is about biology. It is incredibly complex. Second, engineers are really good at trial and error. Engineers will eventually figure out agronomy. It's probably going to take an awful lot of trial and error for them to do that. But I feel a little bit like Paul Revere. The engineers are coming. There are going to be more engineers involved in the agribusinesses. And lastly, I think the agribusinesses of Salinas Valley have really a couple of unique opportunities. One is that this industry understands agronomy. So if agronomy is going to take place in urban locations, why shouldn't that technology be moved from Salinas Valley into those urban areas where that crop will be grown? And of course, the proximity of Silicon Valley to the Salinas Valley, I think, is pretty clear. To be able to combine those two together would be an ideal opportunity. So, to summarize what I've gone over today, really it's the explosion of our population that's driving the emerging technology that we're seeing. How did Tom become a farmer? Well, I think the engineers are coming. And as far as emergent technologies, the incremental innovation is going to give us efficiencies, more efficiencies in agriculture. The disruptive innovation will largely, I think, move food production closer to the consumer. And lastly, there is a great deal of knowledge of agronomy here in this valley, and I believe that can be leveraged to new business opportunities. So, as I was figuring out how to wrap up my talk today, I, of course, went out and Googled. So I Googled the subject of jokes, humor stories, and puns, and agriculture and farming. And I discovered this one, which I thoroughly enjoyed. It's by Leo Kearse. He actually won the 2015 UK Pun Championship with this pun. People who think vertical farms are the solution to world hunger need to grow up. Thank you.
Thank you, Tom. Well done, and a very clever way to end the talk. I like that, a pun. You'll start seeing all of us in the valley start incorporating that as we make the circuit. So